Hi, in this video we start the implementation of our binary search tree. So let's get started. I'm going to create a package with binary search tree data structure. And we are going to have a node. It's going to represent the children, the left child, the right child, and so on. And we are going to have a binary search tree. It's going to represent the tree itself with its nodes, and we will have a class from which we are going to test our data structure. Okay, so let me start with the node. Okay, it's a class node with object. Okay, I'm going to define the constructor in it, and it's going to get a data. So the self.data is equal to data, because this is the essence of binary search tree. We store data in a binary search tree manner in order to be able to operate with logarithmic time complexity. And of course, it's going to have a left child. I'm going to initialize it to none, self.right child, and it is none too. Okay, we are going to have the main operations such as insert, remove, traverse in order, and so on. So let me start with the insert, and I have a data to insert. And as we have seen in the theoretical video, we have to decide that the data we want to insert is greater or smaller than the root of our tree. And if it's smaller, we go to the left child. If it's greater, we go to the right child, and we call our methods recursively, because each subtree has the same property as the whole tree. So if data is less than the self.data, and if not self.left child, which means that if it's if it's null, if it's true, so if not self child, so it's true, it means that the left child is null. I mean none. So we are going to initialize a new node, and else we just have to, we know that we cannot insert our data there because there's a node, so we have to call that insert method recursively with data. Else we have to do the same for the right child. So self.right child, it means that the right child is none, so we have to instantiate it. Else we have to call this insert method recursively on the right child. Okay, we are going to have methods in order to get the minimum value. It's quite easy. So if the self.left, and why the left? Because we know that if something is smaller than the root, it's going to locate on the left child. So we have to check whether the left child is none, and if it's none, we just have to return the self.data, because that's what we are looking for. Else we have to call this getMin method recursively. GetMin value, yes. If not, okay. And it's true for the getMax. We just have to check the self.right child, of course, is none. It means that we return the self.data, and else we return, I think that, yeah, it's not going to work because I have to return. Okay, return the self.rightChild.getMax. Okay, I will have a traverse in order method, which means that traverse in order, it's going to get the numerical sorting of the given set, or if it's strings, it's going to get the alphabetical order. So it's very, very important to know. And we have to check whether the left child, self.leftChild is not none. We self.leftChild, we call this method recursively. Here we just print out the it's going to store integers, for example, but the most important, I think, we can do that self.data, whether it's a double, it's an integer, it's a string, we just don't care about it. And if the right child is not none, we do the same, self.rightChild.traverse in order. Okay, so far so good. These are the most important and basic methods, and a bit difficult is the if you want to remove something. So we have a data to remove. It means that we will have a data and we will have a parent node. So if we have to check whether if we have the data is less than the self.data, first of all we have to search for the given data we want to get rid of. So that's why if it's smaller and if self.leftChild is not none, then the self.leftChild.remove with the data, and parent node is going to be the self, of course. Okay. If the data is greater than the self.data, we have to check whether the if self.rightChild is not, what's the problem? Self.rightChild is not none, then the self.rightChild we have to remove. Why? Because we know that it is not. The data we are looking for is smaller than the self.data, so we keep looking for it. If it's greater, we keep looking for it at the right child. Because we know that this is the main concept of binary search trees, that if it's greater, then it's going to be on the right child subtree. If it's smaller, it's going to be on the left child subtree. And else, we know that it is equal. So, if the self.leftChild is not none, and self.rightChild, rightChild is not none, we know that we have a node we want to get rid of with 2 children. So self.data is equal to self.rightChild.getMin, and self.rightChild.remove with the self.data, and the parent node is going to be the self. elif the parent node dot left child is equal to the self, we have to check whether the self dot left child is not none, and if it's not none, then we are going to denote a temporary node. It's going to be the self dot left child, else the temp node is going to be the self dot right child, and the parent node, of course the parent node is equal to the self dot right child. So it is basically, we want to get rid of the node with two children, so we know that it's not a leaf. And elif the parent node oh, that's a semicolon. Okay, elif the parent node that right child is equal to the self, then if the self that left child is not none, it's kind of scary, but it's not so hard, then the temp node is equal to the self dot left child, else the temp node is equal to the self dot right child, and the parent node is that right child is equal to the temp node. So we just keep updating the references. Okay, and that's all about the remove method. That's by far the most complex method as far as advanced data structures are concerned, because insertion is, I think, quite obvious. The getMin, getMax2, traverse in order 2. So in the next video we are going to implement the binary search tree class together. Thanks for watching.